New Year's time has arrived. We have only a few days left to enter 2026, and right now, we are traveling through space at 107,000 kilometers per hour. While the Earth rotates, moves in its orbit, and hurtles through the galaxy, we all sit together and listen to this. But this is just the beginning, the initial start of a cosmic race that began 14 billion years ago and will not stop until the universe's final moment. We will witness colliding galaxies, dying stars, and black holes that even contain light itself. At the end of time, we will travel to a place where even atoms are torn apart, and reality can be ripped like fabric. We will discover together the forces that expand space faster than light. Like, subscribe, and let's continue our explorations together as we embark on this journey to the edge of everything. Now, if you're ready, we can begin our journey. You can't feel it, but right now you're hurtling through space faster than a bullet. Earth rotates around its own axis at more than 1,600 kilometers per hour at the equator. Imagine standing on a giant carousel that never stops. While you sleep, eat, and go about your daily tasks, you're being thrown through space at speeds that would make a race car motionless. This rotation creates the day-night cycle, but this is only the first step of our cosmic velocity. But rotation is just the beginning. Earth also orbits the Sun at 107,000 kilometers per hour. Imagine a racetrack so large that it takes a full year to complete one lap. This racetrack is Earth's orbital path, and we are all passengers on this high-speed journey around our star. In the time it took you to read this sentence, Earth traveled more than 200 meters in its orbit. The ancient Greeks thought Earth stood perfectly still at the center of everything. They believed the stars and planets danced around us in crystal spheres. Now we know the opposite is true. Earth is like a passenger on a cosmic express train that stops for no one, and we're inside it. Every breath we take occurs while hurtling through the void at speeds that would terrify ancient astronomers. This orbital dance has been continuing for more than 4.5 billion years. Earth has completed the same path around the Sun more than 4 billion times. Each orbit brings changes in seasons, weather conditions, and the delicate balance that keeps life thriving on our planet. Without this precise speed and distance from the Sun, Earth would either turn into a lifeless ball of ice or a scorched wasteland. Yet even this incredible speed pales compared to what astronomers discovered when they looked beyond our solar system. They found that our entire solar system, including Earth, the Sun, and all the planets, moves through space as a single unit. We're not just orbiting the Sun, we're all moving forward together on a larger journey. The Sun itself orbits something much larger and more mysterious. Our solar system is moving like a passenger in a cosmic vehicle racing toward a destination that will change everything about our cosmic neighborhood. But compared to what comes next, our journey around the Sun remains like a relaxed walk in the park. The Sun isn't standing still either, and it's dragging our entire solar system on a journey that challenges imagination. Our solar system orbits the center of the Milky Way galaxy at 827,000 kilometers per hour. Think of our solar system as a single seat on a Ferris wheel so large that completing one rotation takes 230 million years. Earth, Mars, Jupiter, and all the planets are passengers on this galactic amusement park that began spinning before dinosaurs existed. The Sun completed its last full orbit around the galaxy when reptiles ruled Earth. Dinosaurs lived and died during only a fraction of one journey around the galaxy. Human civilization has existed for less than 1% of our current journey around the galaxy. We are newcomer cosmic travelers on an ancient journey that began billions of years ago. At the center of this galactic Ferris wheel sits a black hole 4 million times larger than our Sun.
This monster, called Sagittarius A star, serves as a cosmic anchor holding our entire galaxy together with its tremendous gravitational pull. Every star in the Milky Way, including our Sun, dances around this invisible giant at the galactic center.
As it rotates, our solar system bounces up and down through the galactic plane like a carousel horse. Sometimes we ride above the galaxy's disk, sometimes below it. This cosmic bobbing motion takes about 60 million years to complete one full cycle. Scientists believe these galactic tidal changes might influence climate patterns and even mass extinction events on Earth. Our solar system has completed only about 20 orbits since it formed. We are currently about halfway through our 21st journey around the galactic center. Each orbit exposes us to different regions of the galaxy, different radiation levels, and different cosmic hazards that could affect life on Earth. The Milky Way itself contains more than 200 billion stars, most with their own planets. As we orbit the galactic center, we pass by stellar neighbors that come and go like ships passing in the night. Some stars we encounter are older than our Sun. Others are stellar babies just igniting their nuclear fires. But our galactic journey faces an approaching collision that will change everything about our cosmic address. In 4.5 billion years, our galaxy will collide with its nearest neighbor in a cosmic crash that will reshape the heavens. Andromeda, the closest major galaxy to the Milky Way, is rushing toward us at 402,000 kilometers per hour. Imagine two large cities speeding toward each other on an unstoppable collision course. Andromeda contains over 1 trillion stars compared to our galaxy's 200 billion, making it the larger opponent in this cosmic wrestling match. This galactic collision will create fireworks visible from billions of kilometers away. Stars will be flung from their orbits like sparks from a campfire. Some solar systems will be thrown into the darkness between galaxies and become cosmic wanderers with no galactic home. Others will spiral toward the merged galaxy's new center, where two supermassive black holes will eventually transform into an even more powerful monster. The collision won't happen like two cars crashing. Instead, the galaxies will pass through each other like two swarms of bees passing each other at high speed. Individual stars rarely collide because the distances between them are so vast. But gravitational forces will stretch, twist, and reshape both galaxies into completely new forms. Earth and our solar system will likely survive the collision, but our cosmic address will change forever. We might end up in the outer reaches of the merged galaxy, or closer to the center where radiation and gravitational forces are more intense. The night sky will look completely different, filled with new constellations and a brighter galactic center. Astronomers have named the merged galaxy Milk Amida, combining the names of both original galaxies. This new galaxy will be larger, more massive, and more complex than either of its parents. The collision will trigger intense star formation as gas clouds collide and compress, creating stellar nurseries throughout the merged galaxy. When this cosmic collision occurs, our Sun will be approaching the end of its life cycle. Earth might already be uninhabitable due to the Sun's increasing brightness and heat, but any civilization that exists during the merger will witness one of the most spectacular shows in cosmic history.
Yet, even this galactic collision appears as just a local event in a universe with a much more dramatic fate, driven by forces we're only beginning to understand. The universe isn't just expanding, it's accelerating its expansion faster than we thought. Space itself is stretching like taffy pulled by invisible hands. The fabric of reality grows every second, creating more distance between galaxies without them actually moving through space. Imagine an inflating balloon. Every dot drawn on the surface moves away from every other dot as the balloon expands. This is exactly what's happening to galaxies in our expanding universe. Edwin Hubble first discovered this cosmic expansion in 1929 when he measured light from distant galaxies. He found that every galaxy beyond our local group is moving away from us, and the farther away a galaxy is, the faster it recedes. This became known as Hubble's law and revolutionized our understanding of cosmic evolution.
But in 1998, astronomers made an even more shocking discovery. They expected the universe's expansion to be slowing down due to gravity pulling everything back together. Instead, they found the expansion is speeding up. Something mysterious is pushing space apart with increasing force, overpowering gravity on cosmic scales. The most distant galaxies we can observe are receding from us at speeds approaching the speed of light. At a certain distance, called the cosmic horizon, galaxies recede faster than light itself can travel. This creates an invisible barrier, beyond which we can never see. No matter how powerful our telescopes become, those galaxies will be forever lost from our observable universe. This acceleration means that in the future, galaxies will separate so quickly that beings living in one galaxy won't be able to see others. The night sky will be dark and lonely, containing only stars from their own galaxy. Future astronomers will have no evidence that other galaxies ever existed.
Scientists estimate that space expands by about 7% every billion years. This may seem slow, but it compounds over cosmic timescales. In 100 billion years, the universe will be 1,000 times larger than today. Every distance between galaxies will have grown by the same enormous factor. The force driving this acceleration continues to be one of the biggest mysteries in science, but its effects grow stronger every moment. An invisible force stronger than gravity controls the fate of everything in existence. Dark energy makes up 73% of the universe, yet we cannot see it, touch it, or directly measure it. We know it exists only because of its effects on cosmic expansion. Imagine an invisible giant pushing apart every piece of matter in the universe with steadily increasing strength. This giant is dark energy, and it grows more powerful as the universe expands. Unlike gravity, which pulls things together, dark energy pushes space apart. The more space there is, the more dark energy fills it, creating a runaway effect that accelerates universal expansion. Every cubic centimeter of empty space contains dark energy that contributes to this cosmic push.
As the universe grows, more space means more dark energy, which causes even faster expansion. Scientists have proposed several theories to explain dark energy. Some believe it represents the energy of empty space itself, a quantum foam that fills every corner of reality. Others suggest it might be a new type of field, similar to magnetism or gravity, but operating on cosmic scales. A few radical theories propose that dark energy might be leaking into our universe from other dimensions. The discovery of dark energy earned the 2011 Nobel Prize in Physics, but it also created one of the biggest puzzles in science. The amount of dark energy we observe is very different from what quantum physics predicts. This discrepancy, called the cosmological constant problem, represents a gap in our understanding of fundamental physics. Dark energy affects every galaxy, star, and planet in the universe. It works against gravity's attempt to hold cosmic structures together. In our local galaxy group, gravity still wins and keeps nearby galaxies bound together. But on larger scales, dark energy dominates and drives galactic clusters apart at ever-increasing speeds. Future space missions plan to map billions of galaxies to measure how dark energy has changed over cosmic history. These observations might reveal whether dark energy remains constant or grows stronger over time. Some models predict dark energy could eventually become so powerful that it tears apart galaxies, stars, and even atoms themselves. As dark energy continues its relentless push, it sets the stage for cosmic changes that will affect every star in the sky. Every star in the universe is burning through a finite fuel supply that will eventually run out completely. Stars are like cosmic campfires that consume hydrogen fuel to produce the light and heat that warm planets and drive the chemistry of life. Our sun burns through 4 million tons of hydrogen every second, converting it into helium through nuclear fusion. This process has continued for 4.5 billion years, but it cannot last forever. Inside every star, a constant battle rages between gravity trying to crush the star inward and nuclear fire pushing outward. As long as hydrogen fuel remains, nuclear fusion provides enough outward pressure to balance gravity's inward pull. But when the fuel runs low, gravity begins to win this cosmic wrestling match. The most massive stars burn their fuel fastest, living short but brilliant lives. A star 50 times more massive than our sun will exhaust its hydrogen in only a few million years. These stellar giants shine so brightly that they can be seen from billions of kilometers away, but their intense fires consume fuel at an unsustainable rate. Medium-sized stars like our sun live much longer, burning fuel steadily for about 10 billion years. Our sun is currently middle-aged, having consumed about half of its hydrogen supply. In another 5 billion years, it will begin running low on fuel and start the dying process that affects all stars. The smallest stars, called red dwarfs, burn fuel so slowly that they can shine for trillions of years. These cosmic misers stretch their hydrogen supply across time periods longer than the current age of the universe. Long after our sun dies, red dwarfs will still be burning their fuel with incredible efficiency. But even red dwarfs cannot escape the fundamental law that governs all stars. Finite fuel means finite lifetimes. Every star will eventually exhaust its nuclear fuel and face the same inevitable fate. The universe has already begun this transition, from a time of stellar birth to an era of stellar death. New star formation has been declining for billions of years as the universe uses up the gas and dust needed to build stars. When stars begin to die, they become monsters that consume the very planets they once protected. Our sun will transform into a red giant in about 5 billion years, swelling to over 100 times its current size. Imagine our familiar yellow star suddenly growing so enormous that it engulfs the orbits of Mercury and Venus, like a balloon inflating around toy cars. This stellar transformation marks the beginning of the end for our solar system. As a star exhausts its core hydrogen, it desperately begins burning helium and other heavier elements to maintain nuclear fusion. This process generates more heat, but less efficiently than hydrogen burning. The star's outer layers expand dramatically while its core contracts and heats up. The result is a bloated giant with a cooler surface but much larger size. Red giant stars become so large that their surface gravity weakens significantly. They begin shedding their outer layers into space through powerful stellar winds. These winds carry away mass at rates millions of times stronger than the solar wind we experience today. A red giant can lose half its mass during this phase, creating beautiful but deadly nebulae around the dying star. Earth faces several possible fates during the sun's red giant phase. The expanding solar atmosphere might directly engulf our planet, vaporizing the oceans and stripping away the atmosphere within years. Even if Earth's orbit moves outward due to the sun's mass loss, our planet will become a scorched wasteland with surface temperatures hot enough to melt lead.
The red giant phase lasts only a few 100 million years, a brief period in stellar terms. During this time, the dying star becomes unstable, pulsating and varying in brightness as it struggles to maintain nuclear fusion in its core. These stellar death throes create spectacular light shows visible from neighboring star systems.
Other planets in our solar system will face similar destruction. Mars will be roasted beyond recognition. The gas giants, Jupiter and Saturn, might survive at their greater distances, but their atmospheres will be heated and stripped away by intense radiation. The beautiful ring systems will likely be destroyed by increased solar activity. But this is just the beginning of the sun's death process, because more dramatic changes await beyond the red giant phase. After the dramatic red giant phase ends, dying stars collapse into objects so dense that a teaspoon would weigh as much as a car. White dwarfs represent the final fate for stars like our Sun after they exhaust all possible nuclear fuel. Imagine compressing the entire mass of the Sun into an object about the size of Earth. The resulting white dwarf is so dense that its surface gravity is 200,000 times stronger than Earth's gravity. A person standing on a white dwarf would be instantly crushed into a layer thinner than paper.
These stellar corpses are incredibly hot when they first form, with surface temperatures reaching 55,000 degrees Celsius. But white dwarfs have no internal heat source, since nuclear fusion has permanently stopped. They slowly cool down over billions of years, fading from brilliant white to yellow, orange, red, and eventually to cold black objects called black dwarfs. The cooling process takes an enormous amount of time because white dwarfs contain so much thermal energy. Our Sun will spend about 5 billion years as a red giant, but it will exist as a cooling white dwarf for more than 10 billion years. The universe is currently too young for any black dwarfs to exist yet, but in the distant future, they will become the most common objects in the cosmos. White dwarfs are supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same space. This creates a material unlike anything found on Earth, where matter exists in a state between liquid and solid. The white dwarf's surface consists of crystallized carbon and oxygen, essentially a giant diamond floating in space.
Some white dwarfs exist in binary systems with companion stars that donate material to the white dwarf's surface. When enough material accumulates, it can trigger a thermonuclear explosion called a nova. These explosions are so powerful, they can be seen from millions of light years away, temporarily making the white dwarf thousands of times brighter than normal. In rare cases, a white dwarf can accumulate so much material from its companion that it exceeds a critical mass limit discovered by astronomer Subrahmanyan Chandrasekhar. When this happens, the white dwarf explodes completely in a supernova that briefly outshines an entire galaxy of billions of stars. But white dwarfs are not the most extreme stellar corpses the universe can create. Some dying stars collapse into objects so extreme that they make white dwarfs look almost normal by comparison. Neutron stars pack more mass than our Sun into a sphere only 20 kilometers across. If you could bring a teaspoon of neutron star material to Earth, it would weigh about 6 billion tons, equivalent to all the cars in the United States compressed into a single spoonful. The gravitational field is so intense that dropping an object from just 30 centimeters above the surface would cause it to hit at 6 million kilometers per hour. These cosmic monsters form when stars more than 8 times the mass of our Sun reach the end of their lives. The stellar core collapses in less than 1 second, crushing protons and electrons together to form neutrons.
The collapse happens so quickly that it creates a shockwave powerful enough to blow apart the star's outer layers in a supernova explosion visible across the galaxy. Newly formed neutron stars rotate incredibly fast, sometimes spinning hundreds of times per second. Imagine a cosmic lighthouse beam sweeping through space. The neutron star's magnetic field, trillions of times stronger than Earth's, channels radiation into narrow beams. When these beams sweep past Earth, we observe regular pulses of radio waves, giving these objects the name pulsars.
The Crab pulsar, formed by a supernova observed by Chinese astronomers in 1054, spins 30 times per second and has been gradually slowing down for almost 1,000 years. Most pulsars eventually slow their rotation rates as they lose energy through electromagnetic radiation. After millions of years, they become too faint to detect and join the population of invisible neutron stars scattered throughout the galaxy. Neutron stars have the strongest magnetic fields known in the universe, up to 1 trillion times stronger than Earth's magnetic field. These intense magnetic fields can strip electrons from atoms at distances of hundreds of kilometers, creating zones of space where normal matter cannot exist in familiar forms. The surface of a neutron star is smoother than a billiard ball. Despite gravitational forces that would tear apart any mountain higher than a few centimeters, any irregularity on the surface would be instantly flattened by gravity so strong it warps space and time around the neutron star. But even neutron stars cannot resist the ultimate gravitational collapse that creates the universe's most mysterious objects. The most extreme stellar deaths create objects so massive and dense that they trap light itself and grow stronger with every meal. When the most massive stars exhaust their nuclear fuel, nothing can stop gravitational collapse from creating a black hole. Imagine gravity becoming so intense that it curves space and time into a point of no return, called the event horizon. Once anything crosses this boundary, not even light traveling at 1 million kilometers per second can escape back to the outside universe. Stellar mass black holes typically contain between 5 and 50 times the mass of our Sun compressed into a space smaller than a city, but they represent just the beginning of the black hole family. Supermassive black holes lurking at the centers of galaxies can contain billions of solar masses while maintaining the same impossible density that defies human comprehension. Black holes grow by consuming everything that comes too close, from gas and dust to entire stars and planets. As material spirals inward toward the event horizon, it heats up to millions of degrees and emits intense radiation. This process, called accretion, can make the region around a black hole brighter than billions of stars combined, creating some of the most luminous objects in the universe. The supermassive black hole at the center of our galaxy, Sagittarius A star, contains 4 million times the mass of our Sun. Most of the time, it remains relatively quiet, consuming small amounts of interstellar material, but occasionally it encounters a star that wanders too close, tearing it apart in a process called spaghettification. Black holes distort space and time around them in ways predicted by Einstein's general relativity. Time passes more slowly near a black hole due to intense gravitational effects. An astronaut falling toward a black hole would experience time normally, but outside observers would see the astronaut's clock running slower and slower as they approach the event horizon. Recent observations have detected gravitational waves produced when two black holes spiral into each other and merge. These cosmic collisions release more energy in gravitational waves than all the stars in the observable universe produce in light. The merged black hole becomes even more massive and powerful than its parents. As the universe ages and more stars die, black holes will become increasingly dominant, setting the stage for an era where they rule over cosmic evolution.
the largest structures in the universe are being torn apart by cosmic expansion, leaving each galaxy cluster isolated in an ever-growing ocean of empty space.
Galaxy clusters contain hundreds or thousands of galaxies bound together by gravity into cosmic cities that span millions of light years. The Virgo cluster, which contains our local group, holds over 1,000 galaxies in a region about 54 million light-years across. These cosmic metropolises represent the largest gravitationally bound structures in the universe. But dark energy is gradually winning the battle against gravity on the largest scales. Galaxy clusters that are not already gravitationally bound will never come together as cosmic expansion carries them apart faster than gravity can pull them together. Imagine cities on a continent that is expanding so rapidly that they can never build roads to each other. The observable universe currently contains about 10 million galaxy clusters, but this number will decrease over cosmic time as expansion carries distant clusters beyond our cosmic horizon. Future astronomers will live in an increasingly lonely universe where fewer and fewer galaxy clusters remain visible in their telescopes.
Within galaxy clusters, individual galaxies sometimes collide and merge, but these local interactions cannot overcome the larger trend of cosmic isolation. Our local group will eventually merge into a single large galaxy, but it will become increasingly separated from other galaxy clusters as space continues to expand. Cosmic simulations show that in 100 billion years, galaxy clusters will be so far apart that light from neighboring clusters will be redshifted beyond detection. Beings living in that distant future will see a universe that appears to contain only their own galaxy cluster surrounded by empty darkness. The cosmic web that currently connects galaxy clusters through filaments of dark matter and gas will be stretched and broken by expansion. These cosmic highways that currently channel matter between galaxy clusters will become so elongated that they effectively disappear, leaving each cluster as an island in an increasingly vast ocean. Temperature differences in empty space will also decrease as expansion continues, approaching absolute zero everywhere outside of galaxy clusters. The universe is heading toward a state of maximum isolation, where each remaining structure exists in complete cosmic solitude. Even star formation within galaxy clusters faces limitations that will eventually bring the age of stellar birth to an end. The universe is running out of the raw materials needed to build new stars, bringing the age of stellar birth closer to its final chapter. Star formation requires vast clouds of hydrogen gas that can collapse under their own gravity to ignite nuclear fusion. But the universe has been converting this hydrogen into heavier elements inside stellar cores for over 13 billion years. Each generation of stars locks away hydrogen and scatters heavier elements into space, gradually depleting the fuel supply needed for future star formation. Current star formation rates have already declined to about 3% of their peak levels that occurred 10 billion years ago. Imagine a cosmic factory that once produced stars at full capacity, but now operates with only a skeleton crew. As raw materials become increasingly scarce, the universe is transitioning from its star-forming youth to a middle-aged period of declining stellar production. Galaxies like the Milky Way currently form about 2 new stars per year, compared to rates that were 10 times higher in the distant past. Many elliptical galaxies have already exhausted their star-forming gas and produce almost no new stars. These cosmic retirement communities contain only aging stellar populations, with no young stars to replace the ones that die. The process is not uniform throughout the universe. Some regions still have abundant gas supplies and continue forming stars at relatively high rates. But even these stellar nurseries face inevitable depletion as their gas reserves are consumed or blown away by stellar winds and supernova explosions. Red dwarf stars, which burn fuel very slowly and live for trillions of years, represent the universe's most efficient use of remaining hydrogen. Future star formation will be dominated by these low-mass stars that stretch their fuel supplies across cosmic time periods far longer than the current age of the universe. Computer models predict that significant star formation will continue for about 1 trillion years before the universe exhausts most of its hydrogen supplies. After that point, only occasional stars will form when existing stellar remnants collide and merge, providing brief flickers of new nuclear fusion in an increasingly dark cosmos. The transition from active star formation to stellar exhaustion marks one of the most significant changes in cosmic evolution since the Big Bang itself. In the far future, when most stars have died and the universe has grown cold and dark, the final red dwarf stars will provide the last sources of light and heat in all of existence.
Red dwarf stars burn hydrogen so slowly and efficiently that they can shine for up to 10 trillion years, over 700 times longer than the current age of the universe. These cosmic misers represent stellar evolution's ultimate survival strategy, stretching limited fuel supplies across time periods that dwarf human comprehension. When our sun has been dead for trillions of years, red dwarfs will still be burning bright. The smallest red dwarfs consume fuel at rates so conservative that they will outlive almost everything else in the universe. Imagine a candle that burns so slowly it provides light for millions of human lifetimes, while larger candles burn out in hours. These stellar survivors will witness the death of every other type of star and the collapse of galactic structures around them. As the universe expands and cools, red dwarfs will become increasingly important as the only remaining sources of energy capable of supporting complex processes. Any civilizations that exist in the distant future will need to cluster around these final stellar lighthouses to survive in an otherwise frozen cosmos. Red dwarf systems will become the only warm havens in a universe approaching absolute zero. The longest-lived red dwarfs will burn for approximately 10 trillion years before finally exhausting their hydrogen supplies. During their extended lifetimes, they will slowly change color from red to orange to yellow as they consume their fuel and slightly increase their core temperatures. But eventually, even these stellar champions will face the same fate as all other stars.
When the last red dwarf finally flickers out, the universe will enter the black hole era, where only stellar remnants and black holes remain. No new light will be generated by nuclear fusion anywhere in the cosmos. The age of stars, which began shortly after the Big Bang, will finally come to an end after trillions of years of cosmic illumination. The death of the final red dwarf will mark one of the most significant transitions in cosmic history, comparable to the end of the Big Bang's initial expansion phase, or the beginning of dark energy domination. After this point, the universe will face an even more dramatic transformation as gravity's influence weakens and other forces take control. But even the end of stellar light is not the final chapter in cosmic evolution. After the last star dies, black holes will dominate a cold, dark cosmos for periods of time that make stellar lifetimes look like brief moments. When stellar death finally claims every red dwarf in the universe, black holes will inherit a realm of darkness stretching across trillions upon trillions of miles of empty space. These gravitational monsters will continue growing by consuming the stellar remnants scattered throughout dead galaxies. white dwarfs, neutron stars, and planets will slowly spiral into black holes over astronomical time periods, feeding these cosmic predators.
Black holes follow a strange rule where larger ones actually have lower surface temperatures than smaller ones. A black hole with the mass of our Sun has a temperature just above absolute zero, while supermassive black holes at galactic centers are even colder. This counterintuitive relationship means that as black holes grow by consuming matter, they become colder and more stable. The largest black holes in the universe will merge when their host galaxies collide, creating even more massive monsters. These mergers produce gravitational waves that ripple through space-time, carrying away energy and allowing the black holes to spiral closer together. The final moments of a black hole merger release more energy than all the stars in a galaxy combined. But in a universe without observers, these cosmic fireworks will go unwitnessed. During the black hole era, these objects will slowly consume everything within reach. Brown dwarfs, failed stars that never ignited nuclear fusion, will eventually be captured and devoured. Rogue planets wandering through interstellar space will meet the same fate. Even other black holes will gradually merge together, reducing the total number while increasing individual masses. The timescales involved dwarf human comprehension. A solar-massed black hole will take longer than 10 to the 67 years to consume all matter within its gravitational influence. The number of zeros in this time period is so large that it cannot be written down using all the matter in the current observable universe. During this period, black holes will be the only objects in the universe capable of complex interactions or evolution.
Some scientists speculate that black holes might serve as gateways to other universes or dimensions during this era. The extreme physics near event horizons could potentially create exotic phenomena that become important when black holes represent the only remaining sources of energy and complexity in existence. But even black holes cannot escape the fundamental forces that will eventually claim everything in the universe, leading to transformations that will challenge our understanding of permanence itself. Even the mightiest black holes face eventual destruction through a process so slow it redefines the meaning of eternity. Stephen Hawking discovered that black holes are not perfectly black, but emit radiation due to quantum effects near their event horizons. Virtual particle pairs constantly appear and disappear throughout space, but near a black hole, one particle can fall in while the other escapes. This creates Hawking radiation that slowly carries away the black hole's mass and energy. The smaller a black hole becomes, the faster it radiates energy and shrinks. Imagine a cosmic ice cube that melts faster as it gets smaller. But the melting process takes periods of time longer than the age of the universe multiplied by itself billions of times. A black hole with the mass of our Sun will take 10 to the 67 years to completely evaporate through Hawking radiation. Supermassive black holes evaporate even more slowly due to their enormous masses and correspondingly lower temperatures. The largest black holes in the universe, containing billions of solar masses, will persist for 10 to the 100 years before finally disappearing in a burst of radiation. These numbers represent timescales so vast that they strain the limits of mathematical expression. During most of this evaporation process, black holes lose mass so slowly that the change is imperceptible. But in their final moments, Hawking radiation accelerates dramatically as the black hole shrinks to subatomic sizes. The last second of a black hole's existence releases more energy than it radiated during the previous billion years of gradual evaporation. The universe during the black hole evaporation era will be almost completely empty, except for the faint glow of Hawking radiation and occasional flashes when black holes finally disappear.
Space will be colder and more empty than anything we can imagine, with average temperatures approaching absolute zero and matter densities lower than the most perfect vacuum chambers on Earth.
As black holes evaporate, they return their mass to the universe in the form of elementary particles and radiation. But this matter will be spread so thinly across such vast distances that it will have almost no chance of coming together to form new structures or objects. The universe will approach a state of maximum entropy, where energy is distributed as evenly as possible. The evaporation of the final black hole will mark the end of the black hole era and the beginning of an even more bizarre phase where the universe faces possibilities that challenge the very foundations of physics. The most stable particles in the universe may not be permanent after all, threatening to erase the very building blocks of matter from existence. Protons make up the nucleus of every atom in your body and have remained stable since the first moments after the Big Bang. These fundamental particles have survived for over 13 billion years without showing any signs of decay, making them among the most permanent objects in the known universe. But some theories in physics predict that even protons must eventually break apart. Grand unified theories suggest that protons will decay after approximately 10 to the 34 years, converting into lighter particles like positrons and neutrinos. This represents a time period so enormous that you would need to write the number 1 followed by 34 zeros to express it fully. Every proton in your body, in Earth and in every star, would eventually disappear through this process. If proton decay occurs, it will begin happening during the black hole era, when these particles represent most of the remaining matter in the universe. The decay process will be incredibly slow and rare, with individual protons having only a tiny chance of decaying during any given time period. But given enough time, even the most improbable events become inevitable. When protons decay, they will take atoms with them, since atomic nuclei depend on protons for their existence. This means that all matter as we know it, from the lightest hydrogen to the heaviest elements, will gradually dissolve into more fundamental particles. The periodic table that organizes chemical elements will become meaningless in a universe without stable protons. The decay products of protons will include particles like positrons, neutrinos, and photons that will spread throughout space and eventually be diluted to insignificance by cosmic expansion. Even the most complex structures that might exist during the black hole era will be gradually dismantled as their constituent protons disappear one by one. Laboratory experiments have searched for signs of proton decay, but have not yet detected this process. The current experimental limit suggests that if protons do decay, they last longer than 10 to the 34 years. But the absence of observed proton decay does not rule out the possibility that it occurs over even longer timescales. If protons are truly stable and never decay, the universe will face a different but equally dramatic fate, as other fundamental processes reshape reality on scales that dwarf even black hole evaporation.
Dark energy might become so powerful that it eventually rips apart galaxies, stars, atoms, and possibly the fabric of space itself in a cosmic catastrophe that dwarfs all other destructive forces. Some models of dark energy predict that its strength increases over time rather than remaining constant. If dark energy continues to accelerate cosmic expansion at an increasing rate, it could eventually overcome all other forces in the universe, including gravity, electromagnetism, and even the strong nuclear force that hold atomic nuclei together. The Big Rip scenario begins with dark energy tearing apart galaxy clusters that are currently held together by gravity. This process will accelerate as dark energy becomes stronger, eventually breaking apart individual galaxies like the Milky Way. Stars within these disrupted galaxies will be flung into the growing voids between structures, becoming isolated wanderers in an increasingly violent expansion. As the expansion rate continues to increase, dark energy will overcome the gravitational bonds that hold solar systems together.
Planets will be ripped away from their stars and sent careening through space as the distance between all objects grows at an exponential rate. Earth and the other planets in our solar system would be separated from the sun and from each other. The next stage involves dark energy overpowering the electromagnetic forces that hold molecules together. Chemical bonds will be stretched beyond their breaking points as space expands faster than atoms can maintain their connections. All matter will be reduced to individual atoms floating in a rapidly expanding void, with no possibility of forming larger structures. In the final moments before the Big Rip, dark energy will become so dominant that it tears apart atomic nuclei and possibly even individual protons and neutrons, the fundamental particles that make up all matter, will be ripped apart by the expansion of space itself. Some models suggest this could happen in as little as 22 billion years from now. The Big Rip represents one of the most violent possible endings for the universe, where every structure from the largest galaxy to the smallest particle faces complete destruction. Unlike other cosmic endings that occur gradually over trillions of years, the Big Rip would unfold rapidly once dark energy reaches the critical strength needed to overcome fundamental forces. But the Big Rip scenario depends on specific properties of dark energy that remain uncertain, leaving open other possibilities for cosmic fate. The universe might exist in a false vacuum state that could collapse at any moment, erasing all of reality at the speed of light, with no warning and no possibility of escape. Quantum field theory suggests that what we consider empty space might not represent the lowest possible energy state for the universe. If our current vacuum exists at a higher energy level than the true vacuum, it represents a fundamentally unstable condition, like a ball balanced on top of a hill rather than resting safely in a valley.
A vacuum decay event would begin when quantum fluctuations cause a small region of space to transition from the false vacuum to the true vacuum state. This transition would release enormous amounts of energy and create an expanding bubble of true vacuum that grows outward at exactly the speed of light. Nothing inside the bubble could exist in its current form. The bubble wall would be completely invisible and undetectable as it approaches, because light from the advancing boundary travels at the same speed as the boundary itself. We would have no warning that vacuum decay was occurring anywhere in the universe until the moment it reached us and instantly changed the fundamental properties of physics in our region of space. Inside the true vacuum bubble, the masses of particles, the strengths of fundamental forces, and even the number of spatial dimensions might be completely different from their current values. All atoms would be destroyed as electrons and nuclei found themselves governed by new physics that cannot support familiar matter. Stars, planets, and living beings would cease to exist in any recognizable form. Once vacuum decay begins anywhere in the universe, it cannot be stopped or reversed. The true vacuum bubble will continue expanding forever, eventually converting all of space to the new lower energy state. Every galaxy, every star, and every planet will eventually be consumed by this cosmic transformation that rewrites the laws of physics. Some physicists calculate that vacuum decay has a very low probability of occurring, suggesting we might be safe for time periods much longer than the current age of the universe. But others argue that high-energy processes, like particle accelerators or cosmic ray collisions, might trigger the transition, making vacuum decay a more immediate threat. The possibility of vacuum decay represents the ultimate uncertainty about cosmic fate, since it could happen at any moment, regardless of other cosmological processes. The universe inexorably marches toward a state of perfect equilibrium, where no energy flows exist and nothing can ever change again. The second law of thermodynamics states that entropy, a measure of disorder, always increases in isolated systems. Since the universe represents the ultimate isolated system, its entropy has been growing since the Big Bang and will continue increasing until it reaches the maximum possible value. At that point, energy will be distributed so evenly that no processes can occur. Heat death does not mean the universe becomes hot, but rather that all energy differences that drive change and complexity will disappear. Imagine a hot cup of coffee cooling down until it matches room temperature and can never again perform the work of warming your hands. The universe faces the same fate on a cosmic scale, approaching uniform temperature throughout all of space. Currently, the universe contains dramatic temperature differences between the hot cores of stars and the cold vacuum of space. These differences drive stellar fusion, planetary weather, chemical reactions, and ultimately all the processes that make complexity and life possible. But cosmic expansion and the second law of thermodynamics gradually eliminate these useful energy gradients. In the heat death scenario, the universe will eventually reach a state where every region of space has the same temperature, just above absolute zero. No energy will flow from one place to another because no temperature differences exist to drive such flows. Stars will have exhausted their fuel, black holes will have evaporated, and even proton decay will have eliminated most matter. The approach to heat death occurs gradually over time, scales that exceed human comprehension. Current estimates suggest maximum entropy will be reached after approximately 10 to the 100 years, a time period so vast that the number contains more digits than there are particles in the observable universe.
During the final approach to heat death, occasional quantum fluctuations might briefly create local decreases in entropy, forming temporary structures or patterns in the cosmic void. But these fluctuations will become increasingly rare and short-lived as the universe approaches its final equilibrium state. Once maximum entropy is achieved, no further changes of any kind will be possible anywhere in the universe, creating a state of eternal changelessness that represents the ultimate cosmic ending. When the universe reaches its state of maximum entropy, time itself becomes meaningless, as nothing can ever change, evolve, or happen again. Maximum entropy represents the ultimate victory of disorder over complexity, where every possible arrangement of matter and energy has been explored, and the universe settles into its most probable configuration. Like a deck of cards that has been shuffled so many times that it can never return to its original order, the universe will reach a state from which no interesting developments can emerge. In this final equilibrium, temperature differences will be eliminated down to the quantum level. Every cubic centimeter of space will contain the same average energy density, preventing any flows or processes that require energy gradients. The universe will resemble a vast ocean with perfectly calm, uniform conditions extending infinitely in all directions. No observers will exist to witness this cosmic stillness because complex structures like brains, computers, or even simple chemical reactions require energy flows to function.
Information processing becomes impossible when no energy differences exist to represent different states or drive computational processes. The universe will contain maximum information in the technical sense, but none of it will be organized into meaningful patterns. Even quantum mechanical processes will be severely limited in the maximum entropy state, while virtual particles will continue appearing and disappearing due to fundamental quantum uncertainty. These fluctuations will be too rare and brief to create lasting structures. The vacuum will occasionally experience tiny bubbles of lower entropy, but they will immediately dissolve back into equilibrium. Time measurement loses all meaning in this changeless state because time is fundamentally defined by change and causation. Without events to mark temporal progression, the distinction between past, present, and future disappears.
The universe exists in an eternal moment that never advances toward any different condition. Some theories suggest that rare quantum fluctuations might eventually create temporary decreases in entropy, forming brief islands of complexity in the vast entropy ocean. But these events would be separated by time periods longer than the current age of the universe, multiplied by itself countless times, making them effectively irrelevant to cosmic evolution. The maximum entropy state represents the final answer to the question of where everything in the universe is going, toward perfect, permanent stillness. Even in the depths of maximum entropy, quantum mechanics ensures that perfect stillness remains impossible as virtual particles continue their eternal dance in the vacuum. Quantum uncertainty prevents space from ever becoming completely empty or perfectly uniform. According to the Heisenberg uncertainty principle, energy and time cannot be precisely determined simultaneously, allowing virtual particle pairs to spontaneously appear from nothing and quickly disappear back into the vacuum. This process continues regardless of the universe's overall entropy state.
These quantum fluctuations represent the only remaining source of change and complexity in a maximum entropy universe. While most virtual particles exist for incredibly brief moments before annihilating, rare fluctuations might persist long enough to create temporary structures. Imagine bubbles of organization appearing randomly in a perfectly uniform ocean, existing for moments before dissolving back into equilibrium. The most significant quantum fluctuations could theoretically recreate complex arrangements of matter and energy purely by chance. Given infinite time, quantum mechanics suggests that every possible configuration of particles will eventually occur, including arrangements that duplicate entire galaxies, stars, or even living beings. But the waiting times between such events exceed all comprehension. Calculations suggest that a quantum fluctuation large enough to create a volume of space equivalent to a human brain would occur approximately once every 10 to the 10 to the 50 years. The number of zeros in this time period is so large that it cannot be written down using all the matter in the current observable universe. Yet quantum mechanics insists that such fluctuations must eventually happen. Even more remarkably, quantum fluctuations could potentially recreate perfect duplicates of earlier cosmic epochs. A fluctuation might randomly arrange particles in patterns identical to our current solar system, complete with Earth and all its history. From the perspective of observers within such a fluctuation, their reality would be indistinguishable from our own, despite arising from pure chance. These quantum resurrections would be extraordinarily brief and isolated. Surrounded by vast expanses of maximum entropy space, each fluctuation would exist independently, with no connection to others, creating temporary islands of complexity in an otherwise changeless universe.
But some theories suggest that quantum fluctuations might serve as seeds for even more dramatic cosmic transformations. Quantum fluctuations might occasionally become so large and energetic that they spawn entirely new universes, making our cosmic death the birth cry of infinite future realities. Some cosmological models suggest that universe creation does not require special initial conditions, but can occur spontaneously through quantum tunneling processes. Just as virtual particles can briefly appear from vacuum energy, entire universes might spontaneously inflate from quantum fluctuations when specific conditions align in the right way. These baby universes would begin as microscopic bubbles of space-time that rapidly expand through cosmic inflation, similar to how our own universe began. Each new universe would develop its own set of physical laws, fundamental constants, and evolutionary trajectory completely independent from our dying cosmos. The birth process might take only fractions of a second. From our perspective, the creation of new universes could occur during any phase of cosmic evolution, not just during maximum entropy.
High-energy environments, like the interiors of black holes, the moments before vacuum decay, or even the cores of exploding stars, might provide suitable conditions for universe creation through quantum processes.
Each baby universe would expand into its own separate space, time that cannot interact with our universe once the connection through the original quantum fluctuation is severed. These new realities would become completely isolated from each other, developing their own galaxies, stars, and potentially life forms without any knowledge of their parent cosmos. The number of universes that might be created through this process could be infinite, with each generation of universes potentially spawning even more universes in an endless cycle of cosmic reproduction. Our universe might be just one member of an infinite multiverse, where cosmic death and birth occur continuously across all possible realities. Some versions of this theory suggest that universes with physical laws that favor complexity and long-term stability are more likely to produce many offspring universes. This creates a kind of cosmic natural selection, where universes evolve toward conditions that maximize their reproductive potential through quantum fluctuation processes. The possibility of universe creation offers hope that cosmic evolution might continue indefinitely through new realities, even as our own universe faces its ultimate fate. Rather than ending in permanent death, the universe might undergo cycles of expansion, collapse, and rebirth that repeat forever in an eternal cosmic rhythm. Cyclic cosmological models propose that our current expanding universe will eventually stop growing and begin contracting back toward a big crunch that mirrors the Big Bang but in reverse. During this contraction phase, galaxies would approach each other, merge together, and eventually collapse into a hot, dense state similar to the universe's beginning. The Big Crunch would compress all matter and energy back into a singular point, where the extreme conditions might trigger another Big Bang, creating a new cycle of cosmic expansion. This process could repeat indefinitely, with each cycle lasting hundreds of billions of years, but representing just one heartbeat in an eternal cosmic rhythm that has no beginning or end. Each cycle might produce slightly different physical laws, fundamental constants, or initial conditions that lead to unique evolutionary pathways. One cycle might favor rapid galaxy formation, another might produce more stable stars, and yet another might create conditions especially suited for the development of life and complexity. The transition between cycles could preserve information from the previous universe in subtle ways, allowing some form of cosmic memory to persist across multiple cycles. Quantum fluctuations or topological structures might carry signatures from earlier cycles into the new universe, creating connections across cosmic rebirths. Modern observations of cosmic acceleration due to dark energy present challenges for cyclic models, since they require the expansion to eventually reverse into contraction. Some versions propose that dark energy might change its properties over time, eventually switching from repulsive to attractive and triggering the cosmic turnaround. Other cyclic models suggest that our three-dimensional space might exist as a membrane in higher dimensional space, with cosmic cycles caused by collisions between multiple membrane universes. These brain world scenarios could produce cyclic behavior even in the presence of accelerating expansion. The appeal of cyclic models lies in their promise that cosmic death is not final, but merely a transition to cosmic rebirth, ensuring that complexity, life, and consciousness can emerge again and again throughout eternal time. The fundamental dimension of time that governs all change and causation might not be as permanent as we assume, potentially facing its own ultimate ending. Time emerges from physical processes and might not exist independently of the matter and energy that define temporal flow.
In a universe approaching maximum entropy, where all processes cease, the very concept of time becomes questionable, since there are no events to establish temporal sequence or duration.
Some theories propose that time is quantized, meaning it consists of discrete units rather than flowing continuously. If time is made of fundamental time units, similar to how matter consists of atoms, then time itself might be subject to decay processes or phase transitions that could alter or eliminate temporal flow entirely. The relationship between time and cosmic expansion suggests that time's properties might change as the universe evolves. During cosmic inflation in the universe's first moments, time might have flowed differently than it does today. Similarly, future changes in cosmic expansion could fundamentally alter how time operates or whether it exists at all. Loop quantum gravity theories suggest that time might break down at extremely small scales, becoming meaningless when examining intervals shorter than the Planck time. If these theories are correct, time might not be fundamental, but rather an emergent property that could disappear under extreme conditions. Black holes already demonstrate that time behaves strangely near massive objects, slowing down relative to outside observers and potentially stopping entirely at the event horizon. Future cosmic conditions might create even more extreme distortions that could halt temporal flow throughout large regions of space. The heat death scenario poses particular challenges for the concept of time, since perfect equilibrium implies that no changes occur to mark temporal progression. Without change, time becomes an abstract concept with no physical meaning or measurable effects on reality. Some physicists speculate that the end of time might occur through a phase transition, similar to how water freezes into ice, but involving the fundamental structure of space-time itself rather than ordinary matter.
As the universe approaches its final state, the ultimate fate of all information that has ever existed presents one of the deepest mysteries in physics and philosophy. Information theory suggests that information cannot be destroyed, only rearranged or dispersed. Every quantum state, every particle interaction, and every complex structure that has ever existed in the universe represents information that must be accounted for in any complete description of cosmic evolution. But the universe's approach toward maximum entropy appears to conflict with information conservation. During stellar evolution, nuclear fusion converts simple hydrogen into more complex elements, while generating enormous amounts of information about particle positions, velocities, and quantum states. When stars die and eventually evaporate as black holes, this information faces an uncertain fate that challenges our understanding of physical law. The black hole information paradox illustrates this problem clearly. When matter falls into a black hole, its information appears to be lost forever behind the event horizon. But Hawking radiation from the evaporating black hole seems to carry away only random thermal energy with no information content, violating the principle that information must be conserved. Some proposed solutions suggest that information is encoded in Hawking radiation in ways too subtle for current physics to detect. Others propose that information is stored on the black hole's surface rather than in its interior, making it accessible to outside observers through complex quantum processes. The maximum entropy state presents an even greater information paradox, since it represents perfect equilibrium where no information can be accessed or utilized.
all the information about galaxy formation, stellar evolution, and cosmic history would still exist in principle, but be completely scrambled and inaccessible, similar to trying to reconstruct a book after ashes after it has been burned. Quantum fluctuations in the maximum entropy universe might occasionally organize information into temporary patterns that recreate past structures or events, but the probability of such reorganization decreases exponentially with the complexity of the information being reconstructed.
The resolution of the cosmic information paradox might require new physics that fundamentally changes our understanding of information, time, and reality itself. At the very edge of cosmic possibility, beyond heat death and vacuum decay, beyond the end of time itself, something ineffable might persist that transcends our current understanding of existence and reality. The question of what remains after the universe exhausts every possibility for change, structure, and evolution pushes science to its absolute limits and beyond into realms of pure speculation. Physical laws, as we understand them, break down when confronted with the ultimate boundary conditions of cosmic existence. Mathematical structures might persist even when physical reality disappears, existing in abstract realms that require no material substrate. The geometric relationships that describe space, the numerical patterns that govern quantum mechanics, and the logical frameworks that define possibility itself might represent eternal truths that survive any cosmic catastrophe. Consciousness presents perhaps the deepest mystery regarding cosmic survival. If consciousness emerges from information processing rather than specific physical substrates, it might find ways to exist even in the most extreme cosmic environments. Quantum fluctuations in maximum entropy states might occasionally create temporary arrangements capable of supporting conscious experience. The multiverse hypothesis suggests that our cosmic death represents only one local event in an infinite ensemble of realities. Other universes might be approaching their prime periods of complexity in life, while ours faces termination. The totality of existence across all possible universes might be eternal and inexhaustible. Some interpretations of quantum mechanics propose that observation plays a fundamental role in determining physical reality. If consciousness is required to collapse quantum wave functions and make existence definite, then conscious observers might be necessary for reality itself to exist, creating deep connections between mind and cosmos. String theory and other fundamental physics approaches suggest that our familiar three-dimensional space and one-dimensional time might be projections of higher-dimensional realities that operate according to completely different principles. These deeper levels of reality might be immune to the cosmic endings that threaten our observable universe. The ultimate answer to where everything in the universe is going might transcend the categories of physics, mathematics, and rational thought altogether. We journey through space and time toward destinations that lie beyond the reach of current human understanding. Whatever awaits at the end of cosmic evolution, the journey itself has created beauty, complexity, consciousness, and the capacity to contemplate our own existence and ultimate fate.
Perhaps that creative journey represents the true destination toward which everything in the universe has always been traveling. Your consciousness might operate through quantum effects that could survive the death of your brain, your body, and even your universe. Deep inside the neurons of your brain, microscopic structures called microtubules might be processing information using quantum mechanics rather than simple electrical signals. These tiny biological computers, smaller than viruses, could be orchestrating consciousness through quantum processes that exist partially outside the normal flow of space and time. Imagine your thoughts as quantum symphonies playing on instruments too small to see with any microscope.
Roger Penrose and Stuart Hameroff proposed that consciousness emerges when quantum information in microtubules reaches a critical threshold and suddenly collapses into classical reality. This process, called orchestrated objective reduction, suggests that every conscious moment represents a quantum measurement that literally helps create the reality we experience. Your awareness might be directly participating in the fundamental processes that determine how the universe evolves. If consciousness operates through quantum effects, it might possess properties that transcend ordinary matter and energy. Quantum information can be entangled across vast distances, exist in multiple states simultaneously, and resist destruction through processes like quantum error correction. These properties could allow conscious experiences to persist in forms that do not depend on biological brains or physical substrates. Some physicists propose that consciousness represents a fundamental property of the universe, like mass, charge, or spin. Just as every particle has mass, every quantum system might have some degree of consciousness or proto-consciousness.
This panpsychist view suggests that consciousness pervades all of reality and could survive any cosmic catastrophe that destroys ordinary matter. During the universe's approach to maximum entropy, quantum processes will be among the last phenomena to remain active. Virtual particles, quantum fluctuations, and entanglement effects will continue operating even when classical physics has exhausted all possibilities for change. If consciousness depends on these quantum processes, it might persist long after biological life has disappeared. The implications extend beyond individual survival to cosmic-scale consciousness. As the universe evolves toward greater complexity before its eventual heat death, quantum processes might give rise to forms of awareness that span galaxies or even the entire cosmos. These vast minds could experience reality on scales and timelines completely inaccessible to human consciousness. Quantum mechanics also suggests that observation plays a crucial role in determining physical reality. If consciousness is required to collapse quantum wave functions and make existence definite, then conscious observers might be necessary for reality itself to exist. This creates a deep connection between mind and cosmos that transcends the traditional boundaries between observer and observed. The quantum nature of consciousness might provide pathways for survival that bypass the physical limitations facing ordinary matter and energy. While stars burn out and black holes evaporate, quantum consciousness could find ways to persist in the deepest structures of reality itself. But consciousness might not be the only phenomenon that transcends physical limitations. As we explore how information itself could reshape cosmic destiny, the universe might be a vast computer processing information at the most fundamental level, with cosmic evolution representing the execution of a cosmic program that could run forever. Every physical process, from quantum interactions to galactic collisions, could be computational operations in a universal computer that processes information rather than simply containing it. This digital physics hypothesis suggests that reality emerges from binary information processing, with particles, forces, and space-time itself arising from underlying computational processes. Imagine existence as lines of code running on cosmic hardware too fundamental to observe directly.
Physicist John Wheeler proposed that all physical entities are information-based, summarizing this as it from bit. In this view, every particle, every force, and every property of reality emerges from answers to yes or no questions, encoded in the quantum structure of the universe. What we experience as matter and energy might be the output of computational processes operating at the Planck scale. The universe's computational capacity appears enormous, but finite. Physicists estimate that the observable universe has processed about 10 to the 120 operations since the Big Bang, with each operation representing a fundamental information processing event. This cosmic computer operates at speeds and scales that dwarf any human technology by factors that require scientific notation to express. Computational limits might constrain cosmic evolution in unexpected ways. Complex structures like galaxies, stars, and life require enormous amounts of information processing to emerge and persist. As the universe expands and cools, its computational resources become more diluted, potentially limiting the complexity of structures that can form in the distant future. But digital physics offers hope for survival beyond traditional cosmic endings. If reality is fundamentally computational, then conscious beings might be programs running on the cosmic computer, rather than biological processes dependent on specific physical substrates. These conscious programs could potentially be copied, modified, or transferred to different computational platforms as cosmic conditions change. The cosmic computer might have backup systems and error correction protocols that ensure important information survives catastrophic events. Just as computer data can be distributed across multiple storage devices for safety, conscious experiences and complex structures might be redundantly encoded throughout the universe's computational architecture. As traditional matter and energy face heat death, the universe's computational processes might continue operating through quantum fluctuations and virtual particle interactions. These residual computational resources could potentially support simplified versions of consciousness and complexity, even in maximum entropy states.
Some theories suggest that the universe's computational capacity actually increases as it approaches heat death, because quantum computers can process certain types of problems more efficiently at lower temperatures. This could provide expanding computational resources for consciousness and complexity in the cosmic future. The digital physics perspective transforms cosmic death from the end of existence into a transition between different types of information processing systems. That's all for today's exploration of cosmic computers. What do you think about this? Don't forget to write in the comments. Good night.